So let's take a look at this in detail. So in this random surfing model, at any page, we would assume random surfer would choose the next page to visit. So this is a small graph here. That's of course an oversimplification of the complicated web. But let's say there are 4 documents here, right? D1, D2, D3, and D4. And let's assume that a random surfer or random walker can be on any of these pages. And then the random surfer could decide to just randomly jump into any page or follow a link and then visit the next page. So if the random surfer is at D1, then with some probability the random surfer will follow the links. Now there are 2 outlinks here. One is pointing to D3, the other is pointing to D4. So the random surfer could pick any of these 2 to reach D3 and D4. But it also assumes that the random surfer might get bored sometimes. So the random surfer would decide to ignore the actual links and simply randomly jump to any page on the web. So if it does that, it would be able to reach any of the other pages, even though there's no link directly from D1 to that page. So this is the assumed random surfing model. Now imagine a random surfer is really doing surfing like this. Then we can ask the question, how likely on average the surfer would actually reach a particular page, like D1 or D2 or D3. That's the average probability of visiting a particular page. And this probability is precisely what PageRank computes. So the PageRank score of a document is the average probability that the surfer visits a particular page. Now intuitively, this would basically capture the in-link count. Why? Because if a page has a lot of in-links, then it would have a higher chance of being visited, because there will be more opportunities of having the surfer to follow a link to come to this page. And this is why the random surfing model actually captures the idea of counting the in-links. Note that it also considers the indirect in-links. Why? Because if the pages that point to you have themselves a lot of in-links, that would mean the random surfer will very likely reach one of them, and therefore it increases the chance of visiting you. So this is a nice way to capture both indirect and direct links. So mathematically, how can we compute this probability? In order to see that, we need to take a look at how this probability is computed. So first, let's take a look at the transition matrix here. And this is just a matrix with values indicating how likely the random surfer will go from one page to another. So each row stands for a starting page. For example, row 1 would indicate the probability of going to any other 4 pages from D1. And here we see there are only 2 non-zero entries. Each is 1/2 and a half. So this is because if you look at the graph, D1 is pointing to D3 and D4. There's no link from D1 to D1 itself or D2. So we've got zeros for the first 2 columns and 0.5 for D3 and D4. In general, the element in this matrix M sub ij is the probability of going from Di to Dj. And obviously, for each row, the values should sum to 1, because the surfer would have to go to precisely one of these other pages. Right? So this is the transition matrix. Now, how can we compute the probability of a surfer visiting a page? Well, if you look at the surf model, then basically we can compute the probability of reaching a page as follows. So here on the left hand side, you see it's the probability of visiting page DJ at time t+1. So it's the next time point. On the right hand side, you can see the equation involves the probability of at page di at time t. So you can see the subscript index t here, and that indicates that's the probability that the server was at a document at time t. So the equation basically captures the two possibilities of reaching a dj at time t+1. What are these two possibilities? Well, one is through random surfing, and one is through following a link, as we just explained. So the first part captures the probability that the random surfer would reach this page by following a link. And you can see the random surfer chooses this strategy with probability 1 minus alpha, as we assumed. And so there is a factor of 1 minus alpha here. But the main part is really a sum over all the possible pages that the surfer could have been at time t. Right? There are n pages, so it's a sum over all the possible n pages. Inside the sum, it's a product of two probabilities. One is the probability that the surfer was at di at time t. That's p sub t of di. The other is the transition probability from di to dj. And so in order to reach this dj page, the surfer must first be at di at time t, and then also would have to follow the link to go from di to dj. So the probability is the probability of being at di at time t multiplied by the probability of going from that page to the target page dj here. The second part is a similar sum. The only difference is that now the transition probability is a uniform transition probability, 1 over n. And this part captures the probability of reaching this page through random jumping. Right? So the form is exactly the same. And this also allows us to see why PageRank essentially assumed a smoothing of the transition matrix. If you think about this 1 over n as coming from another transition matrix that has all the elements being 1 over n, the uniform matrix, then you can see very clearly, essentially, we can merge the two parts. Right? Because they are of the same form, we can imagine there's a different matrix that's a combination of this m and that uniform matrix, where every element is 1 over n. And in this sense, PageRank uses this idea of smoothing and ensuring that there's no zero entry in such a transition matrix. Now, of course, this is a time-dependent calculation of the probabilities. Now, we can imagine if we want to compute the average probabilities, the average probabilities probably would satisfy this equation without considering the time index. So let's drop the time index and just assume that they will be equal. Now, this would give us n equations, because for each page we have such an equation. And if you look at what variables we have in these equations, there are also precisely n variables, right? So this basically means we now have a system of n equations with n variables, and these are linear equations. So basically now the problem boils down to solve this system of equations. And here I also show the equations in the matrix form. It's the vector P here equals a matrix, or the transpose of the matrix here, and multiplied by the vector again. Now, if you still remember some knowledge that you've learned from linear algebra, and then you will realize this is precisely the equation for eigenvector, right? When you multiply the matrix by this vector, you get the same value as this vector. And this can be solved by using iterative algorithm. So the equations here on the above are basically taken from the previous slide. So you see the relation between the the PageRank scores of different pages. And in this iterative approach or power approach, we simply start with randomly initialize the vector P, and then we repeatedly just update this P by multiplying the matrix here by this P vector. So I also show a concrete example here. So you can see this now. If we assume alpha is 0.2, then with the example that we show here on this slide, we have the original transition matrix here, right? That encodes the graph, the actual links, and we have this smoothing transition matrix, uniform transition matrix, representing random jumping, and we can combine them together with a linear interpolation to form another matrix that would be like this. So essentially, we can imagine now the web looks like this, can be captured by that. There are virtual links between all the pages now. So the PageRank algorithm would just initialize the P vector first, and then just compute the updating of this P vector by using this matrix multiplication. Now, if you rewrite this matrix multiplication in terms of just the individual equations, you will see this. And this is basically the updating formula for this particular PageRank score. So you can also see, if you want to compute the value of this updated score for D1, you basically multiply this row, right, by this column, and we take the dot product of the two, right, and that would give us the value for this value. So this is how we updated the vector. We started with some initial values for these guys, right, for these, and then we just revise the scores. We generate a new set of scores, and the updating formula is this one. So we just repeatedly apply this until it converges. And when the matrix is like this, where there's no zero values, and it can be guaranteed to converge. And at that point, we will just have the PageRank scores for all the pages. Now we typically set the initial values just to 1/n. Right? So interestingly, this updating formula can be also interpreted as propagating scores over the graph. Right? Can you see why? Well, if you look at this formula and then compare that with this graph, and can you imagine how we might be able to interpret this as essentially propagating scores over the graph? I hope you will see that indeed we can imagine we have values initialized on each of these pages, right? So we can have values here, let's say that's 1/4 for each, and then we're going to use this matrix to update these scores. And if you look at the equation here, this one, basically we're going to combine the scores of the pages that possibly would lead to reaching this page. So we'll look at all the pages that are pointing to this page and then combine their scores and propagate the score, the sum of the scores to this document, D1. So we look at the scores that represent the probability that the random surfer would be visiting the other pages before it reached the D1, and then just do the propagation to simulate the probability of reaching this page D1. So there are two interpretations here. One is just the matrix multiplication, repeatedly multiply the vector by this matrix. The other is to just think of it as propagating the scores repeatedly on the web. So in practice, the computation of PageRank score is actually efficient because the matrix is sparse, and there are some ways to transform the equation so that you avoid actually literally computing the values for all those elements. Sometimes you may also normalize the equation, and that would give you a somewhat different form of the equation, but then the ranking of pages would not change. There is also this potential problem of zero outlink problem. In that case, if a page does not have any outlink, then the probability of these pages would not sum to 1. Basically, the probability of reaching the next page from this page would not sum to 1, mainly because we have lost some probability mass when we assume there's some probability that the server will try to follow links, but then there's no link to follow, right? And one possible solution is simply to use a page-specific damping factor, and that could easily fix this. Basically, that's to say alpha would be 1.0 for a page with no outlink. In that case, the server would just have to randomly jump to another page instead of trying to follow a link. So there are many extensions of PageRank. One extension is to do topic-specific PageRank. Note that PageRank doesn't really use the query information, right? So we can make PageRank query-specific, however. So for example, in the topic-specific PageRank, we can simply assume when the server is bored, the server is not going to randomly jump to any page on the web. Instead, it's going to jump to only those pages that are relevant to a query. For example, if the query is about the sports, then we could assume that when it's doing random jumping, it's going to randomly jump to a sports page. By doing this, then we can bias the PageRank to a topic like sports. And then if you know the current query is about sports, then you can use this specialized PageRank score to rank documents. That would be better than if you use a generic PageRank score. PageRank is also a general algorithm that can be used in many other applications for network analysis, particularly, for example, social networks. You can imagine if you compute the PageRank scores for a social network, where a link might indicate a friendship relation, you would get some meaningful scores for people.